Hey guys, welcome to the Biomechanics 1 video series. This particular lecture is concerned with applied examples around torque that we've spoken about before. I've got two particular examples over here. One is looking at the amount of force required by a muscle in order to keep a weight or a mass of 10 kilograms from rotating downwards. And I'm not lifting it up, I'm just trying to hold it in place. So I have a static equilibrium condition over here that I need to meet. And if you remember from our classes, that static equilibrium, when we talk about rotation, means that the sum of all net torques acting on the system have to equal 0, right? The second example is an exercise example. So in this case, I've got a log that has a particular mass of 20 kilograms, and I'm trying to stop it from rotating down. How much force do I need to exert on the system in order to meet that particular condition of static equilibrium? Again, a follow-up question on this would be, how would I make this easier or more difficult depending on my needs and my abilities? Okay, let's start with this example over here. So something that you guys should remember from our lectures is that torque is defined as the ability of a force to cause rotation. So I'm exerting a certain force, and that force is being exerted a certain distance from the axis of rotation, and it's the angle that I have to also take into consideration, right? So in this particular scenario, I've got a mass that I'm trying to keep stationary. This mass is being accelerated downwards by gravity, so we'll just call this the force of the particular weight. Okay, so you would notice that my axis of rotation over here is my elbow joint, so that would be the pivot point, or the point around which this whole system tends to rotate. And you would notice that this particular mass would cause a clockwise rotation. Alright, from our classes you would note that clockwise rotations are typically given a negative value, but we'll already take care of that with the particular formula that we'll be using. In order to meet the condition of static equilibrium with regards to moments or torques, we discussed the fact that the sum of all anti-clockwise moments or anti-clockwise rotations has to equal the sum of all clockwise moments or clockwise rotations. So I'm gonna start with this particular mass over here. So something that we have to be aware of is that if we're talking about clockwise moments over here, I have to convert a mass into a weight. And how do I do that? I multiply the mass in terms of kilograms by 9.81 meters per second squared, or the gravitational acceleration, right? That's pulling this weight down towards the center of the earth. That's going to create a weight scenario, right, or a downwards pulling force. And I'm going to multiply that by the distance that this particular mass is from my axis of rotation, and that's given here in centimeters. So the thing that I have to do is convert centimeters into meters, because that's my SI unit. So I'll take 35 divided by 100, because it's 100 centimeters per meter, and that's going to give me 0.35 meters. I also have to take the direction in which the force is acting. This particular force is acting perpendicular to my axis of rotation, so I can multiply that by the sine of 90. And in class I've discussed the fact that sine of 90 just simplifies to 1. Alright, so this whole equation would just simplify to this weight force times the distance. Okay, that now has to equal this counter rotation of the muscle force. The muscle has to stop this downwards rotation and would therefore cause an anti-clockwise rotation, right, counterclockwise. But there's a catch, right? This muscular force is acting at an angle, and something that we learned in class is that it's only the component of a force that is acting perpendicular to the axis of rotation that will cause any rotation. So in this, I would have to, technically speaking, add a little perpendicular component of the force, because any force vector can be broken down into its component parts, right? There's a component of this force acting towards the axis of rotation. That's not going to facilitate any rotation. It's only the perpendicular component, or the component of the force acting at 90 degrees towards the axis of rotation. So that's something that I have to take into consideration. Let me just simplify that over here a little bit to make sure everyone knows where it's coming from. So this is the muscular force that I'm interested in, but it's only the component of the muscular force that is perpendicular, right? So this is the perpendicular component over here. Well, since this is opposite the angle, and the angle that I'm given is 60 degrees, my apologies. So this perpendicular component is written as Fm sine theta. If you don't know where I got this or how I got this, please look at one of the videos concerned with trigonometry, but I'll just substitute that in here. Fm sine theta, or in this case theta is 60 degrees, sine of 60 degrees, and I have to multiply that by the distance that this force is acting from the axis of rotation, 5 centimeters, or 0.05 meters. Okay, so then my goal is to isolate Fm, or the muscular force that is required, and what I do is I simply divide both sides over here by the sine 60 times 0.05. Okay, so this all would basically simplify to the following scenario. Once I've taken all of this, let me just copy and paste that actually. So I'm just going to take all of that, and I'm going to copy and paste it over here, and then I'm just going to divide that by this sine 60 times 0.05, just so that we making sure that we're all on the same page, and I should get the final answer of 792.93 newtons, 792.93 newtons, which is approximately equal to 80.8 kilograms. So let's just put that into perspective. In essence, what it's saying is that for me to keep a 10 kilogram weight stationary, or a 10 kilogram mass stationary, my muscle has to exert almost 81 kilograms of force in order to do that, right? So it shows you that this is, technically speaking, an extremely inefficient system, and it's one of the reasons why our joints aren't really designed for maximum force production. They are actually more designed for maximum speed production, but that's another story for another time. For now, bear in mind that it's a much greater force, almost 8 times more force that's required by my muscle just to keep a 10 kilogram mass stationary. Okay, then I have a second example over here. In this particular example, I'm asked how much force am I required to exert to stop this pole from rotating downwards. Okay, very similar setup. What I'm going to do is I'm going to simplify it a little bit more in the following case, that I've just redrawn this pole and the force is acting on this particular pole, right? So I have this downwards mass, which would cause a rotation in this particular direction, which again is an anti-clockwise rotation, meaning that I'm required to create a clockwise rotation in order to stop this from falling down. Okay, let's start with what torque this particular object is creating on the system. Alright, so slightly different example. There's basically two ways to solve this, and I'll start with one that's a little bit different, right? So since this particular mass of the pole is creating a downwards rotation, I could break this into its component parts. So in essence, what I could do is break it down into the components of this particular mass that is acting perpendicular to the axis of rotation, and the component of this mass that is acting towards the axis of rotation, right? That would be similar to what I did in this first example, so it's not the one that I'm going to opt for. I'm going to show you a different way to solve it, which may be a little bit easier. So something else that we learned from the torque equation is this component over here, right, R, which is called the moment arm. So in this scenario, the distance that this downwards force, if I convert this to a weight, is acting from the axis of rotation is 0.5. So that in this scenario is R. But the lever arm is the component of this that is perpendicular to the axis of rotation. So this would be the component of R perpendicular. How do I solve for that? Well, the torque equation would just be slightly restructured, where I have F times R sine theta, where sine theta is the angle between the length R and the force. So it would be this angle up here. Well, what would that angle be? Well, this is perpendicular over here, meaning that R over here is the hypotenuse, and this R perpendicular is the side opposite this angle. So it's not this angle that's given over here. That just gives me the angle that this particular object is orientated relative to the horizontal. It's this angle that I'm interested in. So if this is 90 and that's 30, this angle over here is going to be 60. Alright. So this is going to be R sine 60. Okay, so like we said, this is going to cause a clockwise rotation. So if I use this same principle in this formula, sorry, this is an anti-clockwise rotation. So if I start with that, that particular force is the mass of the object, 20, times the gravitational acceleration, 9.81, right? Times the moment arm, which would be R sine 60, length of R is 0.5, times sine of 60. That again has to equal this clockwise rotation over here, which is going to be Fm times the distance that it is from the axis of rotation, which is given as 0.8 meters, times 0.8 meters. Notice that this particular force is already perpendicular, right, to the axis of rotation, so I don't have to multiply it by sine of 90. That's already given. So then this is fairly easy to solve now. I can just divide both sides by 0.8. So if I'm just going to rearrange this equation slightly, Fm is going to be equal to all of this let's plug it down here, divided by 0.8 meters, and I'm given that that equals 106.2 newtons. Alright, so for me to stop a 20 kilogram pole rotating down, I have to basically exert, give or take, close to 9 kilograms of force. So why are these two examples so drastically different? Here, for me to stop a 10 kilogram weight from rotating, I have to exert almost 81 kilograms of force. Here, I have a mass that is twice as much, but I'm exerting a force that is half as much. Why is that the case? Well, the key aspect here is the fact that the force is much closer to the axis of rotation than the resistance, which is significantly further. So this has a much greater mechanical advantage. In this case, my force is much further from the axis of rotation than the resistance. This brings into play concepts about levers. That's something that I'm going to talk about another time, not something that I want to cover at this specific point in time, but note the difference between the force arm length and the resistance arm length. That's going to give us some clues for later on. The follow-up question was, how do I make this easier? Now, say for example, instead of me applying, how do I make this exercise more difficult? Right? So let's say it's too easy, I'm only having to exert 9 kilograms of force, I want to make this more difficult for me. How can I make this more difficult? Well, let's say for example, instead of me exerting this force at 80 centimeters from the axis of rotation, let's say for example then I start bringing it closer. So instead of over here, I now start bringing it much closer to the axis of rotation. So in essence, I've kept everything the same. I'm not changing the mass of the pole at all. I'm not changing the distance that mass is located from the axis of rotation. I'm not changing the angle at which this pole is orientated, so that's all the same. The only thing that I'm changing in essence over here is the distance that the force is acting from the axis of rotation. I'm bringing it closer. So what we should already see mathematically from this, as this tends to decrease, as the distance from the axis of rotation tends to decrease, the force should increase. So let me just copy and paste that over here. So I copy and paste it, and now we're looking at the secondary scenario where now I've changed this to 0.5. What you'll notice is that the force required increases to 169.9 newtons, right? Or basically 16 kilograms of force. So I've almost doubled the force that's required by me by decreasing the distance from the axis of rotation that I tend to act. And then conversely, how do I make this easier? Well, I can just move further away. That would give me more of an advantage, and I have to exert even less force. Okay, so hopefully that makes some intuitive sense, and you can see how we can start using these concepts of torque and the distances at which I tend to apply a force relative to some axis of rotation, right? In some cases it can be advantageous, and in other cases it can be a disadvantage. Alright, thanks guys.